Hello and welcome to this tutorial presented to you by Lokalise, a translation management system for agile teams. My name is Ilya, and today we are going to explore different character encodings. Well, we as humans, we communicate using natural languages like maybe English or maybe French or maybe Japanese. And of course, when we're using our computers for our daily tasks, we expect to continue using these languages. So you might start your day opening a work chat to discuss the today's tasks with your colleagues, but unfortunately computers do not really understand any of these languages because at their core they operate by using a relatively simple principle. So inside your computer, well, there are central processing units, right, that are called simply CPU. And these CPUs, they execute the instructions in the binary format, my friend. So you can imagine basically a really long tape that is filled with different commands. So that's like a tape that is being processed by your CPU. So it takes instruction after instruction after instruction, well, to achieve some result. So of course it can rewind this tape to jump to a specific instruction, but in a nutshell that's how it works. And in fact this principle remains largely unchanged for the past maybe 50 years or so. But the question is, what is this binary format? Well, simply put, it's all about zeros and ones. So we're representing true and false, yes or no. So I think you get the idea. And so it's crucial to remember that despite the complexity of all the modern systems that we have, we still work with binary logic. So in fact, your CPU can understand only ones and zeros, nothing else. And that's why it cannot understand English or maybe French. And so, of course, this presents a challenge, because humans, well, don't really use binary logic. It's really inconvenient, right? But computers cannot understand natural language. And so we have to, well, somehow marry these two worlds. That's where your character encodings step in, because we use those to, well, translate our text into a format that computers can process and can understand. And while converting text might seem pretty straightforward, because, well, after all, we have been using systems like Morse code for ages, but there are several nuances that we should be aware of. So, well, let's start with discussing a standard that is called ASCII. And to discuss it, we should travel back in time to 40 years ago. The world of IT was simpler back then. The hardware wasn't as powerful, the software wasn't as complex, and, well, to be honest, personal computers were a luxury in many countries. Programmers typically used English characters to write their programs, and moreover, many significant researches and development efforts in information technology were happening in the US. And so it meant that basically people focused on how to accurately represent and encode only the Latin characters, plus some special symbols like maybe dots, exclamation signs, question marks, various kinds of brackets, and so on and so forth. This ASCII standard was introduced in 60s to be used with teletypes. Its concept is really straightforward. Basically, we assign numbers to each Latin character and to some special characters. So, for instance, we can agree that the number 65 represents A, then 66 represents B, and so on. But, well, what about the binary format? The answer is really simple, because we can take these numbers and we can easily convert those to binaries. It's not a problem at all. And so, under the hoods, ASCII used numbers from 0 to 100 227 to encode various characters, specifically codes from 0 to 31 were used for special characters. Some actually were inspired by typewriter functions. So we had a backspace character, new line character, carriage return, etc. But then, starting from 32 to 127, we have like regular characters. So for example, 32 means space. Or maybe 70 means F. Or maybe 102 means F but in lowercase. Actually note, by the way, that lowercase and uppercase is represented by a different code because we have to differentiate those somehow. You can find the full list of all the codes here in this article. So here is the decimal representation and here is the binary representation, and you can see, for example, that 32 is indeed space. Then here is the exclamation mark, quotation mark, etc., etc. So here is the whole list of all the codes that we can utilize. So now we know that these numbers are utilized in ASCII. And you know what it means? It means that any latent character or a special symbol can actually be represented by using only 7 bits of information. Well, to put it simply, 1 bit can contain either 0 or 1. Bit is the smallest piece of information that computers can actually process. And so now, if we have only 2 possible values for every bit, then we can use a special formula written in the following way. This is going to give us 127. This is actually the maximum number that we can represent with 7 bits. So here is this 7. We also should subtract 1 because we are starting from 0 and not from 1. But I think, well, you get my point. Well, if you aren't really into those technical things, you can just believe me that any number from 0 to 127 can fit into 7 bits, because that's important. And while programists could keep things as is, this number 7 is, well, not really convenient, because for one thing, it is not even, and moreover, back in the day, computers could already work perfectly fine with 8 bits of information. And maybe you know that 8 bits equals to 1 byte. And so it made perfect sense to use 1 byte of information for our ASCII standard. But what would it mean in this case? So if we return to this formula and modify it slightly, we are going to get 255. So we can see that by adding a single bit of information, we have increased the numbers in our interval significantly. And in fact, now we can use numbers from 0 to 255, right? And of course, developers have noticed that while numbers in this range are already like occupied for latent characters and for special characters, then numbers from 128 to 255, these numbers are not occupied at all, and thus theoretically these free codes can be used to fulfill your darkest fantasies, basically. But there is a problem, unfortunately, because people tend to have different fantasies. Initially, there was no agreement on what to do with those, extra codes in this range. So, for example, IBM PC used these codes to display, various lines or square root symbols or certain characters with, those diacritic marks like, this one. But computers produced in other countries might have interpreted these codes differently. So, suppose you are in the US and you are preparing your textual document. So you type some regular latent characters plus some characters with maybe diacritics. And, for instance, I don't know, there is a word cafe in your text, just like this. So those are like standard latent characters that fit into this range. but this is like a non-standard character. And it's all perfectly fine until you send this document to a person who is located in, well, another part of the world. Back in the day, the USSR was still, well, pretty much alive, and so if you send this, well, this string to someone who is located in the USSR, and this person opens this document on his own PC, this word would transfer to something pretty strange, actually. So this letter suddenly turns to this. Basically, this is a Cyrillic character that is pronounced as U. So this letter is used in Russian, in Ukrainian, and in some other languages as well. And this is because computers produced in the USSR treated those extra codes in a different way. In fact, there was a separate encoding that is called QA8. It was ASCII compatible, but it treated the extra codes in this range in a different way. So in fact, these extra codes were used to display Cyrillic characters. But then it means that we have no idea how certain codes will be interpreted on different machines, and so indeed it was a big problem. And so to overcome it, specialists introduced a new approach, and this approach was called ANSI code pages. In fact, the American National Standards Institute suggested standardizing these interpretations of the extra code. So they noticed that manufacturers across various countries used these extra codes to denote characters specific to their local alphabets. And so this observation led to the introduction of those code pages. Essentially, we have a consensus on what codes from 0 to 127 represent, so those things remain unchanged. But as for the extra codes, we say that their meaning will depend on the code page that is currently selected on a given computer. And a code page basically acts as a reference table, saying that, well, this number means this character, that number means that character, and so on. Perhaps the most recognized code page is CP1252. It was launched with Windows 3.1 in the beginning of 90s. So it supports the English alphabet, plus some of the European languages, including Spanish, French, Portuguese, German, and so on. So, for example, according to this code page, the code 241 corresponds to this Spanish letter. Whereas for countries using Cyrillic alphabets, Russia, Ukraine, Serbia, and some other countries, they introduced a separate code page that was written as 1251. Whereas maybe in Greece there was also a separate code page with this number. To put it simply, the meaning of those extra codes changed based on what code page is currently enabled on your PC. In theory, it sounds quite nice. But, well, unfortunately, there are problems as well. And the first problem is related to the fact that only a single code page may be active at a time. So it means that working with multiple languages on a single PC, it's not really possible unless you use some really complex and weird approaches. And the second problem was specific for Asian countries because they have many complex hieroglyphs. And for instance, in China, there are literally thousands and thousands of those, hieroglyphs. And as you understand, it is literally impossible to use a single code page to represent thousands of those, because we have only this amount of codes, only 127 codes, right? And so to overcome this problem, they had to encode some characters with 1 byte of information, and some characters were encoded with maybe 2 bytes of information, or, well, 16 bits, as you understand. But this, of course, led to other problems, because if you are not sure how many bits every character occupies, then how are you supposed to move backwards in your text. It was really high time to introduce a new, more reliable standard. And so in the early 90s, specialists introduced a groundbreaking standard that was called Unicode. So the mission was straightforward: to devise a universal set of characters understandable by any computer worldwide, regardless of the location or of the language. So it meant that a computer in America could seamlessly communicate with a computer in Japan without any problems, really. Moreover, Unicode could theoretically be used to represent emoji or even some fictional languages, like maybe languages from Star Trek or Lord of the Rings, etc. So the concept behind Unicode is actually more sophisticated than that of ASCII due to the complexity of languages worldwide. So let's talk about it a bit more. It's clear to us that, well, the latent character A does not equal to maybe B, or it does not equal to C. Well, that's obvious. But at the same time, this latent character does not equal to Cyrillic character that is also written as A. So those look similar, but those are obviously different because they are from different alphabets. Moreover, this character is not similar to A written as lowercase, but at the same time the base meaning of this A remains unchanged regardless it is written maybe in semi-bold or italics, or maybe if it is written with a different color. So this A and this A in orange, it doesn't really matter. Or, well, it doesn't really matter what font are we using, because, well, hello written in Arial is identical to hello written in Helvetica maybe. But does it mean that we can simply ignore all the stylings that are applied to letters? Actually, no, because after all we have discussed that E and E with this diacritic symbol, well, those are not identical, obviously. But in German maybe there is a letter that is written something like that. But can we say that this is just a beautiful letter B? No, of course we cannot, because in fact this letter means two letters S written together. Or maybe in Latvian. Here we have a letter written as K, and we have a letter written like K, but with, this strange thing at the bottom. But can we say that those two letters are similar? No, of course not. Those are different. If you would like to say cat in Latvian, you would write this word in the following way. So it's important to provide this letter here, and it is pronounced as katis, not as kakis. It actually sounds quite funny to locals. And if you think about languages used in Eastern countries, you can understand that the situation is really, really complex. And I'm talking about this so that you understand that in many cases we should store information about how the letter looks and what extra features it contains. It's absolutely crucial. That's why the task that the Unicode inventors had to solve is much complex than it seems initially. And so now the question is how the Unicode works. Well, in fact, they introduce a new concept that is called code points. So a code point looks like this. The U means simply Unicode, then we have the plus, and then we have some number here. Please note that this number is written in hexadecimal, but once again you can convert it to binary easily. You can find various code points on the Unicode website. So you can see, for example, that they have emoji, they have those hieroglyphs. So, for example, this code point means this smiling face. Or maybe the latent character A is encoded in the following way. But wait, in the beginning of this tutorial, we have already learned that in ASCII, the letter A is encoded as 65. Right. So does it mean that the Unicode standard is incompatible with ASCII? Well, not quite, because once again this is a hexadecimal number, and if you convert it to decimal, you will get 65 as well. So in fact, many common characters, specifically latent characters in Unicode, have the same codes as they had in ASCII. But well, for now it seems that Unicode is not too different from ASCII, because once again we have a huge list of codes representing different characters. But it appears that in Unicode you can actually modify your base characters by appending maybe various diacritic symbols to them. So once again, you can take, well, the regular letter E, but then you can say to Unicode, please append the following diacritic symbol to it. So we can write it in the following way. So this is a code point for E, but then there is a separate code point written the following way that represent, this dash that is appended to the previous character, basically. And you can perform as many modifications to your letters as you want. And that's really cool. So you can construct any combination, basically. Well, in fact, many typical combinations, they are already pre-made. So you can use a single code for that. So, for example, you can represent this letter as this combination. Or, in fact, you can use a pre-made code point. But still it's important to note that we can construct as many combinations as we need. And currently there are more than 1 million of code points in Unicode. But in reality this number is not restricted by the standard at all. But there is important thing to mention is that the Unicode standard itself does not state how those code points should be represented in our computers. So in other words, how those hexadecimal numbers should be stored in memory, or maybe how they should be transferred via the internet. And of course, that's also a good question, and people have introduced a handful of different character encodings that implement the base Unicode standard. And the first encoding is called the UTF-8. Also, it is known as UCS2. So this is actually the first encoding, and the idea is really simple. We store every code point as 16 bits of information. That's why you see 16 right here. So maybe, for example, let's take an English word cat. It has the following code points. And to store those code points inside your computer's memory according to this standard, you can use the following approach. So this is a hexadecimal number that occupies 1 byte of information, so together we have 2 bytes of information. That's the idea. But well, here is the deal. No one actually says that we must write all these numbers from left to right. So what I mean is that we can invert every pair. And we can do something like this. And these two approaches are actually known as Big-endian and little-endian. These terms were taken from Jonathan Swift's novel. You can read more about it in the internet, and it's actually an interesting story as well, but well, it is not strictly related to our today's topic. And well, from the theoretical perspective, it makes no difference on how to represent our bytes, like from left to right or from right to left. But some computer architectures historically use Big-endian, whereas some use little-endian. Well, don't ask me why, because once again this is a long story, but well, the fact is that different CPUs might use different endianness. But if we have two ways of representing our UTF-8 encoded strings, then how are we supposed to understand what endianness is utilized in each case? That's actually an interesting question. And to provide this information, specialists introduced a so-called Unicode byte order mark, or simply written as BOM. It was provided in the beginning of the UTF-8 strings, and it could have two possible values, FEFF or FFFE. So the latter means that the bytes have to be basically inverted. And once again, those are hexadecimal numbers. Okay, and so maybe we have solved the problem with endianness. But, well, you might ask another question. Why do I need to store all those extra zeros? Because if you take a look at how the word cat is represented, we can see that for every character there are 2 zeros. Those seem, well, pretty much redundant. Because if we can get rid of all those zeros, then we can use 2 times less space to store the original string, right? And this was especially important for people who used latent characters. Because, well, once again, as long as Unicode is ASCII compatible, it uses the same numbers to represent latent characters. So once again, A is 65 in ASCII and in Unicode as well. And as long as all the latent characters plus some special characters can be easily encoded with numbers from 32 to 127, then it means that they can perfectly fit into 1 byte of information, as we've already seen. But here we can see that we must use 2 bytes of information, which is, well, not optimal. And so another problem is that while Unicode respects ASCII, the UTF-16 encoding is not readily compatible with it. Because as long as we always use 2 bytes of information, it means that in ASCII the character A is represented as 41, well, in hexadecimal, but in UTF-8 the same character is represented as 0041 in hexadecimal once again, and you can clearly see that those numbers are not identical, right? People had lots of old documents that were still encoded in ASCII, and so no one, of course, wanted to convert all those documents for the new standard. And the last concern is that, well, this 16 bits enables us to encode only this amount of characters. So it gives us 65,536 different characters. So it is quite generous, but it is not nearly close to million plus code points that are introduced by Unicode. And so due to all these issues, well, this standard was not too popular and people continued to use ASCII. But then luckily a new encoding was introduced, and it is called UTF8, my friend. It was introduced in the beginning of the 21st century. It also implemented the Unicode standard, but in a somewhat different way. By the way, please note that UTF-8 is not equal to Unicode. So UTF-8 is just a method for encoding the vast number of characters that are defined by the Unicode standard, because sometimes people tend to use these two terms interchangeably, but this is not the case actually. So now the question is how this standard works. So as this number 8 implies, the data is stored in octets, or basically as bytes, because 1 byte equals to 8 bits of information. But we utilize a variable number of octets depending on the actual code point, in contrast to what we had with UTF-16, where we always had 2 bytes of information. So in this standard specifically, code points from all zeros to 007F, which in fact corresponds to this range, those are encoded with a single byte of information, which perfectly correlates to what we had with ASCII. So it basically not only solves the problem with extra zeros that was found in UTF-16, it also makes the UTF-8 compatible with the ASCII format. Then we have code points in this range, and those code points use 2 bytes of information. And so this pattern continues, and with characters requiring up to 4 bytes for code points, okay? And so that's why the UTF-8 standard became really popular for the past couple of decades. But of course, well, there were other standards as well. For instance, there was a standard that was called UTF-7. It is a lesser-known encoding standard that was designed to be compatible with systems only capable of handling 7 bits of data. So unlike UTF-8, UTF-7 ensures that the first bit is always 0. So it's like a workaround for older messaging systems that might strip higher order bits, but well, I don't think this is widely utilized these days. So another example would be UTF-32, which represents each code point with 4 bytes of information. But well, it means that even the simplest latent characters consume significantly more space compared maybe to their ASCII representation, so that's why UTF-32 is not widely popular these days. And so now you can understand that there are many various encodings out there, and it is really important to specify which encoding is currently being utilized for your data. So if you even have some plain text on your computer, well, this text is still encoded with something, basically. And if you have textual information, but you don't know what encoding is utilized, this information is pretty much useless, because you are not sure how to interpret this information. And for example, maybe on web pages, we actually use a special meta tag, and we say that, you know, the encoding for this HTML document equals to maybe UTF-8. And so if the encoding is absent on the page, or if it is defined incorrectly, it might lead to various issues. So for example, if you try to take a UTF-8 string and display it with ASCII encoding maybe CP1252, certain characters will not be displayed at all. And so on websites, they will be replaced with those, you know, question marks looking in the following way. Well, this is because it is impossible to establish parity between certain codes in UTF-8 and ASCII. By the way, you might wonder, so if the HTML document reports its own encoding in the meta tag, how are we supposed to start reading this document? So in other words, to read a document, you need to know its encoding. But to know the encoding, you have to start reading the document. Actually, it's a funny paradox, but well. In fact, the meta tag is usually present at the very beginning of the HTML document, so your browser can start reading this document in good old ASCII. Typically, the HTML preamble contains only latent characters and maybe some special symbols, like maybe these brackets or the equal sign, etc. And so it is safe to start reading as ASCII, but when browser sees the character set on this page, it basically switches your encoding to the one that is requested by the document. But of course, if the encoding is not stated at all, then some browsers might try to guess it, which might lead to some unexpected results. And that's why you should always specify your encoding, my friend. And so this is it for today. I think we have underscored the critical role of text encoding in information technology. We have covered how various encodings work. So that's it for today, folks. I thank you for staying with me, and well, see you in my other tutorials.